Please shut your laptops. The classroom is awfully empty. Today did count for attendance in case you guys didn't realize this, because I announced in the last class that we'd have a class today, right? And so we will be checking the Pokemons, and if you're not, if you don't answer, you will be marked absent. Anyways, there's no point in my telling this to you guys because you're here, but this is for the people who are going to meet. Just watch the video on MediaTek. I know that most of you don't even bother to do that. It's kind of unfortunate. Please shut your laptops. Yeah.
Sometimes I just watch it on YouTube because it's easier.
Pardon me?
Sometimes it's just easier to watch it on YouTube, truthfully, because you guys post it on YouTube.
Yeah, but then you're supposed to be here in class because, you know, this is...
Yeah.
You want to ask questions. If you ask YouTube questions, it's not going to answer you.
Fair enough. Also, I have a quick question that's kind of irrelevant. How did you guys get, like, the list for all the Pokemon names?
You're going to have to ask my TAs about that. I just issue the command and things happen, right? So guys, please shut your laptops. You there, shut your laptop. Yes, all of you. Where did we leave off in the last class? Mara? How to learn parameters of a network. So here's what the actual place where we left off. We realized that training a network is something called empirical risk minimization. What did we mean by empirical risk minimization? Kanpeng. What did we mean by empirical risk minimization here? Okay, he doesn't. Yes, somebody else?
We're minimizing the distance between samples of the training space and
So, good. So why did we call it, yes, Jeffrey, why did we call it empirical risk minimization?
Well, I think it's because I think the empirical risk, is like the expected error between the target function and hypothesis function. And since like our training data is drawn from like the same distribution, that means that like the average error between the hypothesis and target function over the training data is a good approximation for like the expected error.
That's right. So you were saying something? Yeah.
Yeah, something similar. I'm trying to say that because we only have a finite amount of data points across the in each domain of the function that we're trying to approximate.
Yeah.
We can only minimize the difference between our neural network function and these finite given data points, and we're using that as an approximator to true error.
So we call it AMP first. What was the N? What was the actual objective function we would have liked to minimize? Anybody else? Shreyas, what was the actual objective function you would have liked to minimize? Yeah, so the lady at the back, you raised your hand. Yeah.
I think the error.
So, and how did we define the error? It was the integral. You wanted the entire area. You wanted the difference, the volume of the difference between the predicted function and the actual function to be minimized. But this we could not minimize directly because you don't know the actual function. So instead we are minimizing the error over a finite number of average error over a finite number of samples, and hence, because we are only minimizing the error over what we observe, we call it an empirical risk. It's an empirical risk minimization problem, yes.
All right, so let me try to get something straight, sir. So basically, like the true error is like the basically the sum of like the error between the true error is like the total like error between like the hypothesis function and
yeah. So this is the true error we wanted to minimize. We didn't actually get to see this, so we just took the average over a bunch of samples that we had obtained. These are observations. They're empirical observations. That's what we minimize. So we're performing empirical risk minimization.
What's the expected error, sir?
The expected error is the area of the shaded area weighted by the probability of x, right? So that's what we wanted to minimize. So we're minimizing the empirical risk over the drawn samples, and since the x's are given, it's a function only of the network parameters. And so this is an instance of function minimization, optimization. So we're going to spend some time talking about function minimization. Now, before I continue, somebody raise a hand? I need one. Okay, thank you. Okay, you raised your hand. All right. When I speak of the derivative of a function y equals f of x with respect to x, what do I mean by the derivative of y with respect to x, Priyanka?
If x changes any small amount, how much would y change?
Those are words. Can you, if I want to put that in math, how would I put it? That's correct.
F of x minus delta of x, limit delta x tends to 0, f of x minus delta of x plus f of x.
F of x plus delta x.
Minus f of x divided by delta x.
Okay, perfect. Is this how all of you learned what a derivative was? Does this always hold?
No,
When doesn't it hold?
when the function is not differentiable. So
Assume the function is differentiable. Yes.
Would it be when x is a vector?
If x is a vector, there's no such thing as dividing by a vector, right? So the definition still holds, but when we speak of differentiable functions, when I have a function of this kind, if I take any point, as I zoom in closer and closer and closer, eventually at that point it's just going to be a bit of a line, right? And so the way we actually define derivatives is a multiplicative factor alpha that multiplies any increment, tiny increment in x delta x to give you the corresponding increment in y. That's the only way to actually define derivatives. If your standard definitions will break down under some conditions, right? And so a derivative of a function at any point tells us how much a minute increment in the argument changes the actual value. It's a multiplicative term that multiplies the increment in x to give you the corresponding increment in y. Now have this burned into your head because we're going to use this a few times in the next few classes. So, all right, the gentleman at the very back with your hands like so, how do you define a derivative? Yes?
A derivative is from a variable changes in small amounts with respect to another variable.
No, so the person behind you, yeah, he was, yes, okay. Can you repeat that? How did we define derivative?
The corresponding change in the function becomes.
We actually, I just gave you the definition, guys. It can't be like, remember less than half a second. I said it's the multiplicative term that multiplies a small increment in x to give you the corresponding increment in y, right? I just asked you to repeat what I told you. So I'll do this sometimes just to make sure you're paying attention. Yes?
How does this work, like, if the dimensions of y and x are different?
Let's see. Okay. So when x is a scalar, then you're saying, okay, how much does a small change of x result in a small change of y? I'm assuming y is a scalar. And then in this case alone, as x goes to 0, you can write this as dy over dx, or more appropriately as f prime of x. First, I don't think this is a great notation. Why?
It's not actually.
It's not?
It's not division.
It's not division, because if x is a vector, you can't divide by d of x, right? Why is this a better definition? F prime of x. Somebody.
it represents a function which.
It depends on x, right? The derivative itself depends on x. The slope depends on where you're measuring it, okay? So the derivative is the rate of change of the function of x. It tells you how much a small increment in x will result in change in y. If it's a large value, it means the function's changing fast. If it's a small value, it means the function is changing slowly. And if a small increment of x increases y, is the derivative positive or negative? And if it decreases y, it's negative, right? I'm speaking of scalars at this point. And similarly, if a small decrement in x, if the derivative is positive, If I decrease x, what will happen to y?
Decrease.
It decreases. If the derivative is negative, it increases, right? Simple things, right? And at maxima and minima, the derivative is going to be 0 if the function is nice and smooth. Why? Because as you approach a maximum, the function is going to increase slower and slower and slower. Eventually, it stops increasing, then it turns and begins to decrease. So maxima and minima are what are called turning points because the function turns. At a maximum, regardless of which direction you arrive at it from, the function is going to keep increasing. Once you cross it, it's going to begin decreasing. At a minimum, it's the exact opposite, right? Now, to answer someone's question here, what if the argument is a vector? So I still have y equals f of x, but x is now a vector. And just, for notation's sake, I'm going to say x is a column vector. So what does delta x look like if x is a column vector? It's going to be a column vector also, right? And so delta x is going to be a column vector of delta x0 through delta x minus 1. This definition still holds if y is a scalar, right? So for this definition to still hold, what will x alpha have to be? Can you speak up, please? A row vector, right? That's the only way that the product is going to be a scalar. So you're going to have delta x0 through delta xn minus 1. So correspondingly, you're going to have alpha 0 through alpha n minus 1. This is going to be delta y, which I can write it as alpha 0 delta x0 plus alpha 1 delta x1 and so on. That makes sense to everybody so far? So this is how I'm going to define a derivative. The dy over dx definition doesn't really hold. It's the multiplicative factor that multiplies the small increment in x to give you the corresponding increment in y, okay? If y is a vector, the same equation applies entry by entry for y, which is why the derivative will be a matrix. Okay, we'll talk about this later, okay? Questions?
This is colloquially called a Jacobian, right? Or is
This is not a Jacobian, right? This is a derivative, right? So let's go one step further, and there's nothing colloquial about the term Jacobian. It's very formal. We'll talk about it later, right? And so I have delta y equals alpha 0 delta x, x0 plus alpha 1 delta x1, and so on. What is alpha 0? So now, when I'm speaking of a delta x, it means a small increment in x. In a multidimensional space, if I'm at any point x, is there only one direction in which I can take a step? No. I can take a step in any direction, right? Delta x can be pretty much any which way. So one of the possibilities of delta x is where I change only one variable and set all the other variables to be fixed. So if I just keep this and set all of these to 0, this is going to tell me how much y changes when all the other variables except x0 are fixed and only x0 is incremented by a small amount. And that is what is known as the partial derivative of x with respect to x0. And so the entries of this derivative, alpha, are the partial derivatives of the variable with respect to each of the elements of x. And so overall, delta y is going to be the sum over all components of the product of the partial derivative of y with respect to the corresponding component and the increment in that component, right? So I can rewrite it like so. I'm going to use this notation for my derivative, the inverted triangle called the nabla. It's the derivative of y with respect to x. I may change notation for other things later, but for now, that's what we're going to hold. And so this is a row vector comprising the partial derivatives of y with respect to x. Now, how many of you have heard the term gradient? So how do you define the gradient?
It's the sum of.
Same thing as slope.
Same thing as? No, okay. So
It's a slope.
the gradient is, what do we mean by slope? This is a multidimensional function.
It's a sum of partial derivative in every
Direction.
So the gradient is simply defined as the transpose of this derivative. So if I have an x component vector, the derivative row vector, column vector, the derivative is an x component row vector. What will that gradient be? And then if I have an n component variable, right, x, the derivative is an n component row vector. The transpose of it is an n component column vector. And so delta x is going to be delta x0 through delta xn minus 1. And the gradient, which is transpose, the gradient is the transpose of the derivative, is going to be, the vector of partials, right? And how many components will the gradient have? Anybody? As many as the original vector itself. So the gradient lives in the same space as x. And so when I write it this way, right? Here's the derivative. It's a vector of partial derivatives. The gradient is the transpose of the derivative. And so let me just write this as g for simplicity, right? So delta y equals g dot delta x. It's the inner product between the gradient and the delta x, right? So, but then the gradient is simply a vector of partial derivatives. What does it mean? What is the gradient? Do you have any feeling for what the gradient could be? Yes?
Shows you how the output function y would change as every component is nudged by a little bit.
That it does, right? But then is there more to it than that?
It is in the direction of the maximum slope in that space.
Okay, why is that? What do you mean by maximum slope?
All the components are proportional to the partial derivatives, right? So if the output changes very little in that direction, this gradient will not point in that direction very much, right? So
okay, you need a bigger sign, man.
sorry.
Ayush, okay. So Ayush is right. So let's look at this. This is an inner product, the delta y is an inner product between the gradient and delta x. What do we know about inner products? What is, if I have two vectors u, what is u and v, what is u transpose v? This is simply mod u, mod v, cos theta, right? So if I have two vectors u and v with an angle theta between the two, the inner product is just the magnitudes of the two vectors times cos theta. So this is a vector inner product, and to understand its behavior, let's look at the behavior of inner products. I have u and v. I have fixed u. I'm changing v. The v is the one in blue, and you can see how the inner product changes as the angle of v changes with respect to u. And when is the inner product largest? When the two are perfectly aligned, okay? So again, delta y, which I'm calling, for small enough increments, I'll call that dy, or in this case df, because f is the function, is the inner product between the gradient and the increment, right? And once again, I can take an increment dx in any direction, but only one of these directions is the gradient. So what does this tell me? Yeah.
It's sort of a tangent to the function?
No. So basically, what this really tells me is that if the increment I take is in the same direction as the gradient, that's when the function is going to change fastest, right? Because the inner product between the increment, between the gradient and delta x is going to be the maximum when delta x points in the same direction as the gradient. That makes sense to everybody? Right? So if that is the case, if I have at any point, the gradient lives in the same space as x. It's going to be a vector in the x space. Taking a step delta x along the gradient, I can take a step delta x in any direction. And anytime I take a step delta x, it's going to change y. But if the delta x is aligned with the gradient, that's when the function y increases fastest. So moving in this direction increases f of x fastest. Which direction must I move in for f of x to decrease fastest?
Negative.
The exact opposite, right? Moving in this direction decreases f of x fastest. And now, if I get to the maxima and minima, what is the gradient going to be? Anybody? Yeah.
The gradient will be in the same direction if you want to go towards the maxima.
No, but if I'm at the minimum, what will it be? It's going to be 0. Because right at those points, the derivative is going to be 0. But moving in any direction doesn't change anything, right? And so, there's another property the gradient has. If I slice the function, you get an edge. These edges are called, at any particular height, you get an edge. This edge is what is called a level set. This is the set of all x's, which give you the same value of y. And the gradient at any x is going to be orthogonal to this level set. It's easy to prove, I won't go into it. There's also a second property of derivatives called the Hessian. What do you mean by the Hessian? Anybody know? Is there an eraser here? Yeah, here it is. Okay, here's what a Hessian means. Now, what does one know about the second derivative of a function? If I have a scalar function, what does one know about the second derivative of a function? Anyone? Yes. Somebody answered on Zoom. Can you repeat? Can you speak up, please?
It's going to be 0.
0 what? No, what is the second derivative of a function? It's the rate at which the derivative itself changes, right? So let's keep this thought in mind. This Hessian is a second derivative matrix where the ijth entry is the derivative with respect to xi and xj. And first, let's have this poem. So I don't know who's Hariyama? Yes, okay. Is that first statement true or false?
True.
Okay, beautiful. And who's Cubone? C-U-B-O-N-B-O-N-E.
Hi, I am.
Cubone. Okay, second statement true or false?
True.
True. Okay. And who's Swallowed? S-W-A-L-O-T?
Yes, I'm here. The third one is true.
Third one is true. Okay, second question. Who is Moltres? M-O-L-T-R-E-S. Moltres here? Moltres is absent, okay. Who is Wigglytuff? W-I-G-G-A. Okay, Wigglytuff. What about the first what is the answer to the second question?
Scalar.
It's a scalar. Y is a scalar function of an n cross 1 column vector. What is the derivative of y?
It's going to be a 1 by.
It's going to be a 1 cross n row vector, right? And so here are the answers. The first two statements are true. The gradient is not the derivative of f of x with respect to x. What is the gradient? The transpose of the derivative of x with respect to x, f of x with respect to x, okay? And so here we are, back to our problem of optimization. We're trying to find a minimum or a maximum of a function. We know the derivative there is going to be 0. So how do we do this? Now, when you were given a function and asked to minimize it in school, how did you do it, Liv? Okay, when I gave you a function in school and asked you to minimize it, how were you taught to minimize it?
Find the minimum, take the derivative and find 0.
Okay, would that be sufficient, finding where the derivative is 0? What else do you need to do? Yeah.
You need to know the second derivative.
You need to know the second derivative, right? The derivative is 0 at a turning point, but this is not necessarily a minimum. Here's a poll. Okay, this is an easy one, so I'm not going to give you very much time. Who's Houndoom? H-O-U-N-D-O-O-M.
It says that the pole number 308 cannot be found on Piazza.
Can be found on Piazza? It's there, yeah. Okay, who's Houndoom? Houndoom's absent, right?
Wait, I think that might be me or Houndor. I'm not sure.
Okay, let's assume it's you, right? You're present.
Okay.
Okay, what is the answer?
I think it's 3.
3, right? F prime of x is 0 and the second derivative is positive. So all right, guys, shut your laptops, please. And so this is what we had. Both maxima and minima have 0 derivative. Both are turning points. But when you look at the maxima, as you approach it, initially the derivative is positive. And then, but it is less and less positive till it arrives at the maximum. Then it becomes increasingly negative. At the minimum, the derivative is initially negative, but then it's less and less negative. It becomes 0, then it becomes increasingly positive. So this is what the derivative looks like, the red curve. Becomes 0 at the maxima and minima. And so the second derivative, you can see, what is the slope of this guy? At a maximum, this derivative goes from positive to negative. At a minimum, it goes from negative to positive, right? And so the second derivative is negative at maxima and positive at minima, and this is the test you used in school, yes?
There's another part when it doesn't change, it just hits the 0, and then if it's like.
Yeah, there are all kinds of exceptional cases, but this is a generic case, right? And so here's what we did. Find the value at which f prime was 0. That's a turning point. Then you check the second derivative and determine if it was a maximum or a minimum, right? Now, this doesn't always work. At maxima, the derivative is 0. At minima, the derivative is 0. But then you have inflection points where the functions may be decreasing, then it slows down and just stops. Then continues decreasing, right? So at that point, it's not really a minimum, it's just sort of locally flattened. So and so at those points, the derivative is still 0, but if you check the second derivative over here, the second derivative here is going to be negative at the maximum. The second derivative here is going to be positive at the minimum. At the inflection point, the second derivative remains 0. So even this check wouldn't necessarily work. So there are other things you'd have to be checking, particularly in the case of multidimensional functions, multivariate functions, right? So when you have a function of multiple variables, the optimum is still a turning point. Shifting in any direction will change the value. And so for smooth functions at the minimum and maximum, the gradient is going to be 0. And so the simple thing for you to do is just compute the gradient of the function and find the location where the gradient is 0. So very simple. I can just write out the formula for the gradient, equate it to 0, I solve it. I just told you what a Hessian matrix is. Now, what is the Hessian? If I plot any function, let's say I have a bowl-shaped function of this kind in 2 variables, then I can approach this point from multiple directions, right? And so there is a direction in which it gets here fastest, and then there's another direction along which it gets there second fastest. So you have these principal directions of curvature. And so over here, regardless of whether I'm coming along this direction or this direction, this guy remains a maximum, right? So if I took a second derivative as I walked along this direction, what will the second derivative be at this point?
Negative.
It's going to be negative, right? If I walked along this point, walked in this direction, what's it going to be? Yeah. Okay, guys, give me a Pokemon. Nobody's answering, right? So what is the second derivative? So Lairon, L-A-I-R-O-N, right? What would the sign of the second derivative be if I approach this maximum along this direction? Yes?
Still negative.
Still negative. Lairon you're not Lairon, right? No. So Lairon is absent. Now suppose I had a function of this kind. Then the directions of, the principal directions of change are going to be these two. So if I walked along the first direction of change, what is the second derivative going to be at the minimum?
Positive.
What about the second direction?
Positive.
Also positive, right? Now here's another function, which is a something like this. It looks like a saddle, right? Over here, if I walk in this direction, this is a minimum. If I walk in this direction, that is a maximum. But the derivative at that point is 0, right? So the two principal directions along which the function changes fastest are these two. And what would the second derivative be if I walked along this direction at this point? But if I walk this way? Right. So the Hessian matrix, the eigenvectors of the Hessian matrix give you the principal directions along which the function changes most. And the eigenvalues give you the second derivative along those directions. And so if the function is a strict maximum, all the eigenvalues of the Hessian function, Hessian matrix are going to be negative. If it's a strict minimum, all the eigenvalues are going to be, what are they going to be? And something like this. One of them is going to be positive and one of them is going to be negative. And so you can compute the Hessian matrix of the candidate solution, check the eigenvalues. If all of them are positive, it's a minimum. If all of them are negative, it's a maximum. If they are mixed, then it's probably a saddle point. Yes?
There seems sort of a way to like apply like the second derivative rule to like basically multivariate derivatives.
That's pretty much it, right? The Hessians are just, because you have multiple directions along which you can approach these points, the Hessian captures the principal directions and the curvature. Yes?
Came up with the second derivative in the direction.
So you did understand this bit, right? You did. So the same thing over here. So let's say, look at this function here. If I slice it in the vertical direction, what is the slice going to look like? It's just going to look like this, right? If I slice it in this plane, it's going to look like that. So over here, when you walk in this direction, over here, the second derivative is positive, and here it's negative. That makes sense? Right? And those directions are captured by the eigenvectors of the Hessian matrix, right? So this is how you'd solve it, but then often it's not possible to simply solve for this because the function is ugly. In fact, it's if you just randomly drew a function, then with a probability of 1, it does not have a mathematical form that you can actually comprehend. This is easy to prove. Anybody who's done real analysis knows this to be true. And so most functions cannot be just written down and have them differentiated, and you cannot equate those derivatives to 0 to get a solution. So here, you're going to take a different strategy. You're going to guess the minimum. You're going to start off at some point and say, okay, I think this is the minimum. But then you find it's not. So then you take a step to a place maybe it's where it's better. Check again, and then keep doing this. So if you want, until you get to a point where you think the function is a minimum. But in order to do this, first you need to know which direction to step in and how big a step you must take, right? So for this, there's a very simple principle that we can follow. Now, let's say I have a function of this kind, like so, and my initial guess is here. Is this a minimum?
Nope.
So which way do I go? To the right. How do I know this? You see that if I increment x a little bit, the function decreases, right? What does that mean? If I increment x, y decreases. What is that? The derivative is negative, right? So I can just check the derivative. If the derivative is negative, I have to increase x. If my initial guess is here, a small increase in x, what will happen? What will it do to y? So what will the slope be? So I can just check the slope. If the slope is positive, I have to go backwards, right? And so that's a very simple thing. At each guess, I can check the sign of the derivative. If the sign is positive, then I have to take a step back. If the sign is negative, I have to take a step forward. Can I just combine those two equations and write it without an if? Anybody? Can I write that without an if? Yes. How?
I think you can put negative of f dash of x.
So I can just factor the sign in right here, right? And multiply my step size by the sign. I still haven't specified what the step size is. And so if the derivative is positive, then I'm taking a step back. If the derivative is negative, minus and minus become plus, I'm taking a step forward. This captures both of them in one function, right? I'm still not clear about how big a step to take. But then for that, we begin looking at functions like these, which are very nice, bowl-shaped. Now, if I'm out here, is the magnitude of the derivative large or small? Come on, guys, say it aloud. Okay, so should I be taking a small step or a big step? Big step, because I'm far away, right? I'm thinking of bowl-shaped functions. If I'm out here, what's the derivative like? I should be taking a small, careful step. So in other words, I want the step size to be proportional to the magnitude of the derivative, assuming it's a bowl shape. And so I can factor that in, and I can just say that I'm going to modify my current estimate by some step size times the negative of the derivative. Right, this is just for a function of a single variable. If I have and you can generalize this to function of many variables.
Isn't that a copy of like an earlier poll?
Is it? It shouldn't be.
Looks suspiciously similar.
It's similar.
Yeah, crazy.
Or maybe I have it wrong. Okay, if it's a copy, then everybody should be able to answer it, right? Especially, so who's drowsy? Okay, what's the answer?
So the answer is that the first and the second is true, and the third is false.
Okay, so thank you, because this is a copy of a previous poll, and you do remember that you've seen this before. Thank you. So at any function, there are many directions in which we can step, such that f of x increases. But the direction of the gradient is the direction in which the function increases fastest, and so if my current guess is over here, and I want to minimize the function, which is my best choice of direction to walk? The direction in which the function decreases fastest, right? What would that be? The exact opposite of the gradient. And so that's why we call it gradient descent. So to find a minimum, at every point you find the gradient and you take a step against the gradient. To find a maximum, you take a step in the direction of the gradient. So this is gradient ascent for maxima, gradient descent for minimum. And what is the step size? There's many solutions to it. So here's how the overall algorithm is going to work. You start at some point, and then you find the gradient, you check the derivative, or you decide if the function is a minimum or not. How do you decide? We'll get to that in a bit. And if you don't think it's the minimum, you take a step. And then keep doing this. So when do you stop? When would you, yes? Mm-hmm. That's a good one.
When you reach the global minima.
How do you know it's a minimum?
When the change is x and the change that you're seeing in the function is way too small.
So that's the correct answer is this. When taking further steps doesn't decrease the function any further. But there's a second step you could have checked, right? How do you check if it's a minimum? You can just take the derivative, right? And check if the derivative is 0. Because you expect the derivative to be 0 at minima. Guess what? That's not a good test. Because you can have minima where the derivative is not 0. Can somebody think of a situation where that happens? Yes?
Would it be more of a computational constraint as we have like different points?
No, that's not. We'll get to it in a bit, right? Hopefully I get to that point in class. So here's the overall gradient descent algorithm, right? I'm going to start off with an initial guess, x0. Then at each x, I'm going to find the direction of the gradient and then take a step against the gradient. And keep doing this till my function doesn't decrease any further. At which point I declare victory and I'm done, okay? Questions? Yes?
Is it when the norm of the rate of change is like less than some epsilon?
Yeah, whenever the function, it's a scalar function at this point, whenever the change becomes smaller than some threshold, you say, okay, I'm done. Now, how will it converge? For nice functions like the one on the top left, which is the kind of function for which we actually designed this whole process, then, when the function is steep, you take large steps. As you approach the minimum, you take smaller, careful steps. And you're guaranteed pretty much to arrive at the minimum. But if you have functions like the one to the bottom, you have all kinds of places where the slope is 0. So you can arrive at local minima, you can arrive at saddle points and get stuck in all of these places. And we'll see in coming classes how to deal with these. So here's a problem.
The other pose is different from the question.
The poll is different from this question? All right, so my apologies. Sometimes this happens. We still have the Pokemons, right? Okay. Who's Surskit? S-U-R-S-K-I-T. Surskit is absent. Okay. Who is Victory Bell? V-I-C-T-R-E-E-B-E-L. Who's Victory Bell? Also absent. Guys. Who's Swablu? S-W-A-B-L-U. Or S-W-A-B-L-U.
Oh, Swablu.
Yes. All right. Okay, who's Skarmory? S-K-A-R-M-O-R-Y.
Oh, that's me.
All right, okay. Can you answer this question?
I think it's exactly opposite to the direction of the gradient at f of x. X is 0.
Perfect, right? You compute the gradient, you take a direction step in the exact opposite direction. And so that's gradient descent. So that was a quick detour into function optimization. But then let's get back to our problem. What was our problem? We were talking about how we would train neural networks, right? And so here's the situation we have again. We are given a collection of training data. The training data consists of input-output pairs. Here's an x, here's the desired output of the function at x. So we always have pairs of input and output, right? And then, show the laptop, please. Yeah, sorry. Okay. And then you compute a loss function. We call it a loss, but it's actually the empirical risk. It's the average divergence over all of the training points. This is a function of just the network parameters, and this is what you're going to minimize with respect to the network parameters. But in order to be able to do this, there are many things that must be defined first. So here's the overall algorithm, right? You initialize W, just follow the gradient descent rule until the loss no longer changes. But here's the problem setup. This is the entire problem as before. Remember, we're working with real world data, right? Images, sounds, text, what have you. Real world outcomes. Here is a class. This is a cat. This is a dog. Neural networks are mathematical objects. They're not going to work on cats, dogs, and images. And so, what are these input-output pairs? How do we specify them? But then there's more. What is this function f? What are its parameters w? What is this divergence function? Without specifying these clearly, you can't specify the loss. There's nothing to minimize. So let's go through this. Let's start with the function f itself because it's the simplest thing of the lot. What was f for us? Anybody? Yeah. Someone said something. Can you say it aloud?
The neural network function.
The function f for us is the neural network, right? It's a feed-forward network. I'm going to be assuming that there are no loops for now. It's a directed network with inputs and outputs, and the parameters are the parameters of the network itself. The way we specify it with the network, we will say is layered. We're going to call the input an input layer, although there are no neurons over there. This is just terminology. The input is called the input layer. All the other layers other than the output are called hidden layers. And then the final layer from which all the outputs are read, that's called the output layer. Mohammed, you've dropped in. Okay. And now, the individual neurons in the network, we need to know what those are. And the way we will define it, generally, the individual neurons can be any differentiable function, because each neuron gets a bunch of inputs and generates an output. But more specifically, we're going to assume something of this kind, where we first compute an affine function of the, first we compute an affine function of the input, and then we, so that gives you this affine variable z, and this affine variable z is then put through an activation function of some kind. So what are these activation functions? So this is what we're going to assume. So the parameters are the weights and the bias. Okay. Now, what is the activation function? In prior classes, we saw, yes.
I just isn't clear. Why is it the case that the functions in the neural net have to be differential? I mean, it's certainly nice for them to be differentiable, but do they have to be differentiable?
If they're, the reason,
If
okay, let's go back and look at how did we, what was the gradient descent doing?
you have to have derivatives.
For every parameter in the network, you're just saying, how much does incrementing this parameter a little bit change the loss? And if incrementing the parameter increases the loss, you decrement it. If incrementing the parameter, decreases the loss, you increment it, right? So you need to be able to compute how much the loss changes with every increment of the parameter, which means the loss must be differentiable with respect to the parameter, which means it must be differentiable with respect to everything within the network.
Yeah, so I could use a different, like a non-gradient based optimization function, then we're back into kind of common for all.
Absolutely. Absolutely, right? So, okay. Here are some classic activation functions. We saw this activation function. This is the threshold activation function, where we said sigma of z is 0 if z is greater than 0, 1 if z is greater than 0, 0 if it's less than or equal to 0, right? What was the derivative of this guy? The derivative of this one was 0 everywhere. It was infinite at 0, and then 0 everywhere else. So this is not a very nice function. Now, there's the smoother version of it, which is the sigmoid, which goes from 0 here to 1 here. It's 1 over 1 plus e raised to minus z. And you can see if z is plus infinity, what is e raised to minus z? Can you say it aloud, please? So if z is infinity, e raised to minus z is 0, minus infinity is 0. This becomes 1, right? If z is minus infinity, then this becomes e raised to plus infinity. So this is infinity. The whole thing becomes 0. In between, it's going to be smooth. So this is what it looks like. What will the derivative of this function look like? The derivative is going to be 0 out here. That's also 0 out here, right? In between, it sort of slowly goes up, and it peaks at 1 over 4. That's what the derivative of this function looks like. You can see that it's flat on both sides, right? So that's, now we like this. That's a sigmoid activation. We really like it because it has an interpretation as a probability. So we use it all the time. Then we also like using the tan-H activations, which is basically the sigmoid centered to go from centered on 0 and stretched so that it goes from -1 to 1. And the sigmoid also, therefore, has the same kind of derivative, except that the peak is 1. Then we also like things like the one at the bottom, right? So this guy, here f of z equals z for z greater than 0, and it's 0 else. So this is going to look like this. How does the derivative of this function look? Anyone? Yeah. What's the derivative?
0 in the negative and 1 in
1 in the positive, right? So again, here this is not a strictly differentiable function because at 0 there's no derivative. Yes, Jeffrey?
I actually have a question about like hypertan and sigmoid. So because they have similar shapes, like the derivatives also have similar shapes in that like they're always increasing, the function's always increasing, so derivatives are always positive. But like the rate of change like basically like decreases after you cross like that 0.
So they have very similar shapes. They just see the derivative is just scaled, that's all. So now this has this nasty property of having a corner. So I can have something that's like this. That's your soft plus. And then what would the derivative of the soft plus look like in this case? It's 0 out here. It's 1 out here, and it's going to be a smoothed version of the sky, right? So the soft plus now actually has a sigmoid as a derivative. So these are different activation functions you can have. Now we have something called vector activations. Now in the typical neural network that we've seen so far, for every perceptron, we first computed a z, which is an affine function of its inputs, and the z was put through an activation, and you got the output y. So within each layer, every perceptron computed its own z and got its own output. Now in this situation, if I modify this z, will this output change?
Yes.
This z only goes through this activation, right? So if I change this z, this output is not going to change. They're independent of one another. So these are what I'm calling scalar activations. But then there are other settings where instead of saying yi equals sigma of xi or zi, I can say the set y0 through whatever yk is a function of z0 through zk, meaning it operates on the entire set of inputs and generates the entire set of outputs. What this means is that if I change any one of these guys can change. And here's an example, the famous softmax. So here what we do is this. We have z0 through zn minus 1. All of them go in to the activation, and you get a corresponding output corresponding to each one. But then we actually, yi is e raised to zi, but divided by j e raised to zj. So what this means is that if you sum all the y's, now the sum of the y's is going to be positive, right? It's going to be 1. And every single y is positive. This making sense? So this begins to look like a probability distribution. Okay. Yeah.
Is the reason why this is a vector activator is it because if you increase one of these, you have to shrink the others to make some of
pretty much, right? So tell me this. If I increase the z0, what happens to y0 using this formula? It increases. What happens to this guy? Decreases. So what is the sign of the derivative of this y with respect to this z? What about these guys? Negative. So just seeing the behavior tells you how the derivatives must be, right? And so this is a vector activation. Now more generally, if I have a bunch of scalar activations, I can still think of the lot as a vector activation, except that the individual perceptrons don't interact. So this is a special case of a vector activation where each z just affects only the corresponding y. But that's just a viewpoint which will help us with math later, right? And so we've defined f. And what are its parameters w? F is a neural network comprised of neurons. The parameters of f are the parameters of the neurons within the network, right? So what are these input-output pairs? Now, given in a training set, you're going to be given x's and the corresponding desired outputs d, and the network must try to compute the desired output, right? So if I have a 10-dimensional input and a 3-dimensional output, desired output, how many outputs must the network have?
3.
3 also, right? Because the network must have as many outputs as the desired outputs, right? And so each training instance, n over here is the subscript n represents the index of the training instance. The input is going to be a vector. The desired output is going to be a vector of some other dimension. And the actual output of the network is going to be a vector of the same dimensionality as the desired output. So let's consider each of these. The input, which is captured by the input layer, that's got to be a bunch of numbers. So whatever your input is, whether it's an image, whether it's text, whether it's audio, whether it's financial market, astronomical charts, I don't care. Eventually, it has to be converted to a vector of numbers. So in the case of images, it can be a vector of pixel values. In the case of audio signals, it can be a vector of features that you derive from it. In the case of text, you still have to convert it to a real valued vector. We'll see how in later classes. In general, the output must be real valued. So we've sort of dismissed the input. We know how to deal with it. What about the output? If the desired output is real valued, meaning it's some real value, this is not a classifier performing regression, then it's just the real value itself, right? If it's a scalar output, then the neuron network is going to have a single output neuron, which is generating real valued numbers. And so the desired output is going to be a scalar D. The network will be generating an output Y. If you're trying to predict a vector, like predicting the stock market, then the desired output is going to be a vector of real values, and correspondingly the network will have as many output neurons as the dimensionality of the desired output itself. Now, if I'm performing binary classification, is this a cat or not a cat? Then what is the desired output? Binary. If I give you a picture of a cat, you want the output to be 1. If I give you a picture of a house, you want the output to be 0, right? So the desired output now is going to be binary. It's either 0 or 1. And how many neurons, output neurons, will the network have? 1. Also 1, right? And so now here's the distinction. I have a network with a single output neuron, whatever, and then it has a single output neuron. The desired output is either 0 or 1. So ideally, the net neuron must be outputting either a 0 or a 1. But in reality, for this neuron, we're typically going to use a sigmoid activation, which gives you a continuous number between 0 and 1. And that can be viewed as the probability of the class 1, given the input. And we'll see in later classes that this is actually a perfectly reasonable interpretation. In fact, the probability of 1 given in the input is what the network actually does compute. And so this indicates the fact that for actual data, in general, a feature value x may occur for both classes, but with different probabilities. The nice thing about this is that this activation is differentiable. We want our activations to be differentiable, right? Now, if I'm performing multi-class classification, not just is this a cat or not a cat, but which class is it, right? So let's say I have 5 classes: cat, dog, camel, hat, flower. This is a bunch of classes. How do I convert them to a vector? So I will arrange them in some canonical order, yes?
Is a one-hot vector like a distribution where like you have 100% probability true class, everything else is 0 probability?
Pretty much, right? So you're going to assign all of the classes in some canonical order. And then the desired output, when the input is any one of these classes, is going to be a vector of zeros for every class except the desired class, for which that is 1. So the one-hot vector represents a very deterministic, very confident probability distribution where you're absolutely certain it's a cat and not anything else. Yes?
Should we like post we do our test, should we like convert it to like 1 through 5 in this case, or whatever values, so we can save memory?
That's an engineering choice, but this is basically this is what is implicitly done, right? I don't need to actually give it a 5-component vector. I can just give it the index of the, actually no, we don't give it, we actually work with 5-component vectors at the output. So the desired output is always going to be a one-hot vector, right? What about the actual network? How many outputs must it have over here?
5 as well, a vector.
As many as the number of classes, right? So I have my network and it's going to have as many as the number of classes. And then if I give it a picture of a cat, this is my cat. Okay, it must give me, this is what you want the output to be. It's absolutely certain that it's a cat. In reality, this doesn't look very much like a cat. So it's not going to generate something that's very confident, right? It's actually going to be, the ideal output must be one-hot. More realistically, it's going to be a probability vector, and we know how to compute probabilities. We use a softmax. And the softmax is going to give, yes?
What if the input is not any of the classes? What will the output be?
So you're pretty much restricted to the list of classes. If it's not any of the classes, then none of the above would be another class.
Like a positive.
Yeah. No, it's going to be, I can add an extra class which is none of the above, right? That would be one. Yeah. There was a hand raised at the back. Did somebody have a question at the back? No. All right. Okay. So in this case, the output activation is going to be a softmax, which can be viewed as a probability, right? And so again, you can see that the sums of the outputs is 1. Every output is positive, so that's a probability distribution. And if the network is properly trained, when it sees a picture of something that's definitely a cat, then the output should be close to 0 for all the non-cat indices and close to 1 for the cat index. Make sense? Right. And so in a typical problem statement, you're going to be given a bunch of training instances, images of digits, along with information about which digit the image represents, for instance. And so now, if you're performing classification, a binary classification would be, is this a 2 or not? In multiclass recognition, it's going to be, which digit is this? And so if you were performing binary classification, here's what your training data are going to look like. Images and a binary label, 0 or 1, depending on whether it's a 2 or not. For multi-class classification, you'd actually indicate the class. But then when you actually train the network, these indices are going to be converted to one-hot vectors with a 1 at the index of the class. Make sense? Right. And so we've defined F, we've defined the input-output pairs. We are left with one last thing. And this is important. This is the divergence. Now, what is the divergence? What did the divergence quantify?
Empirical risk.
Empirical risk, yeah, but yeah.
The difference between the expected and the value that you.
The divergence quantified the error between the actual output of the network and the desired output of the network, right? So if you can't quantify it, you cannot optimize the network. And so this is what we will need. Now, for the loss to be differentiable, this divergence must also be differentiable. We saw this in the last class. If I'm simply counting errors, it's not differentiable. And so that kind of a divergence function is useless. You want something that is actually differentiable. And so that's how we define our divergence. Now, if I am performing real valued prediction, I'm predicting real values, then y is a vector. My desired output d is also a vector. And so I typically define my divergence as half of the squared norm of the difference between the actual and desired outputs. The half over there is a convenience factor so that when I differentiate, the twos cancel out. So we always have the half. You'll encounter this in the quiz, right? And so this is going to be, if I have a vector desired output d with many components, and the network itself is going to have an output y, but also with many components, then the error is simply defined as half of yi minus di squared. Now, what is the gradient of this loss with respect to y? Anyone? Chain rule. No, this is just with respect to the yi's. I don't need a chain rule, right? So the derivative with any respect to yi, you just take the differentiate this, the 2 cancels out the half. But then observe that yi minus d squared is the same as d minus yi squared, right? So is this derivative over here yi minus d, or is it d minus yi? What is it? Anybody? Why is it yi minus d? Yeah, but either way it doesn't work. It gives you the same formula, right? So there is a correct answer. And if you're ever confused, then it's very easy to figure out what the correct answer is by just thinking about derivatives, right? So if d is my desired output, And if y is my current output, is y minus d positive or negative?
Positive.
Where it's positive, right? Will increasing y increase the error or decrease it? Increase the errors. So what is the sign of the derivative?
Positive.
Was positive, which means it must be y minus d, right? Just think this through, and you never need to get confused about whether it's y minus d or d minus y, okay? And so this is the derivative of the divergence. It's a row vector of the differences between the actual and the desired outputs, okay? Now, for binary classification, now you're no longer just looking at a squared norm, right? You need something else. So let's see, I'm trying to determine if it's a cat or not a cat, okay? And if it's this, I'm trying to, this is my classification problem. Is this a cat or not a cat? And then I give you this picture. Which is my cat. And so the desired output is a 1, right, in this case. So this is y, this is p of y. I want the desired output to be out here. So if the network says it's not a cat, if it's absolutely confident that it's not a cat, is it just slightly wrong or infinitely wrong? It's infinitely wrong, right? And if it does say with absolute certainty that it's a cat, that's 100%, the error is 0. So in other words, when d equals 1, you want something like this. Where if it's absolutely certain that it's not a cat, it's infinitely wrong, right? On the other hand, if I give you this picture, okay, that's a house, just in case you didn't know, then the desired output is 0. And if the network is absolutely certain that it's a cat, how wrong is it? Just wrong or infinitely wrong? And if it's absolutely certain that it's not a cat, it's 0, right? And so here you want something like this. And so you want a function that goes to infinity when y is 0 if d is 1, and when y is 1 if d is 0, right? What kind of function will do that? Right here. So it's minus d log y. So see that when d is 0, that minus d goes away. And the second term is minus 1 minus d log of 1 minus y. So when the desired output is 0, this guy goes away because d is 0. And so you're left with the 1 minus d term. And now, so if d is 0 and y is 1, 1 minus y is 0, log of 0 is infinity. So it's infinite. Whereas if y is 0 and d is 0, then 1 minus d is 1. 1 minus y is also 1, right? Log of 1 is 0. Also the other way, right? If the desired output is 1, this term goes away. And then if y is 0, it's infinite. If y is 1, it's 0. So this is a function that actually gives you this very nice property, right? Furthermore, check something interesting.
Professor, is this the only function that does that?
If you can come up with something else, you're welcome to use it, right? But this captures the concept, right? There are other functions which have similar properties. But this is the one we use most commonly. Now, let's say the desired output is 0. Then if you increase y, should the error increase or decrease? The desired output is 0. I increase y. Should the error increase or decrease? Increase. So what should the derivative of the error be with respect to y when d is 0? Positive, right? And so if d is 0, 1 over 1 minus y. Y lies between 0 and 1, it's always positive, right? Now if the desired output is 1, if I increase y, should the error go down or increase? What will the slope be? Negative. You can see that that also holds, right? Minus 1 of 1 over y. And so here is the function. We could have used the quadratic, just like, in the case of the regression. The red curve shows you the quadratic curve. The quadratic curve doesn't capture the spirit of the problem. When you're completely wrong, you see a cat and say, this is absolutely not a cat. You're going to say, I'm slightly wrong. That doesn't really capture it, right? You want this to be infinitely wrong. And so this is the Kullback-Leibler divergence. It captures the idea very cleanly. But then there is an interesting corollary to this. So let's say the desired output is 0. Then what is the derivative of the loss when y is 0? When y is 0. What's the derivative of the loss? Take a look over here, right? If the desired output is 0 and y is 0, what's the derivative? Is it 0?
1.
When the desired output is 1 and y is 1, what's the derivative? -1, right? So even when the answer is right, the derivative is non-zero, which is why when you perform gradient descent, it's not sufficient to simply check the derivative. The derivative can actually be quite significant, and you can still be at a minimum. It makes sense to you guys, right? And so note that when y equals d, the derivative is not 0. So the divergence is 0, but the derivative is not 0. Okay, guys, take a deep breath. We have only 8 minutes left. Please wake up. And I'll give you 5 seconds to take a deep breath. Collectively. Okay. We are done. So for multi-class classification, we're going to use the same thing. Now the output is going to have as many components as the desired output. And once again, you want the same principle. You have 100 classes, right? Let's say. And if the desired output is a cat, and the actual output is a cat, you want the error to be 0. If the desired output is not a cat, if it's one of any of the other classes, and the actual output is a cat, how much must the error be? Effectively infinite, right? And so the way you capture it is that I can just say di log yi. Observe this. If the desired output is 1, and the output is also 1, actual output is 1, log of 1 is 0, this becomes 0. But if the desired output is 1, it's a cat, and the network is absolutely certain that it's not a cat, then this yi for cat is going to be 0. Log of 0 is minus infinity, right? So I need a minus. And so this becomes infinite. You see how this works? And so for the KL divergence, for the multi-class classification, the actual KL divergence formula, you want this to be 0. So it's defined as a summation over all classes, di log di over yi. This is just the math. But then if you work this through, you know that the desired output is always either 1 or 0. So when the desired output is 1, this term becomes 0. Log of 1 is 0. When the desired output is 0, d is 0. So this term always goes away. The second term only remains for the one component for which the desired output is 1. And for that guy, the term is minus log of y. And so the KL divergence, when you're using the one-hot representation of outputs, is simply the negative of the log probability assigned to the correct class. And once again, you want to see that the derivative of the output, of the probability assigned to the correct class, or rather the derivative of the loss with respect to the probability assigned to the correct class must be negative. Anytime you increase the probability assigned to the correct class, the loss error must go down. And so, on the other hand, if you increase the probability of the other classes, it has no influence on the error itself. And so here's the derivative again. It's minus 1 over y for the target class and 0 for everything else. And once again, you will see that when the network is perfectly correct and classifies this exactly as the target class, the slope of the loss is actually not 0. It's minus 1. Okay? And so, once again, even though the divergence is 0, so it's minimum, the slope is not 0. Now, the divergence formula that we will use is the so-called Kullback-Leibler divergence. But then when you do your homeworks, you're going to run into what you call the cross-entropy loss. As it turns out, the cross-entropy loss and the Kullback-Leibler divergence are basically the same thing when you use a one-hot representation. And they're the same thing to within an additive positive term when you're using anything else. So minimizing the cross-entropy loss will minimize the KL divergence. Okay. Now, one last term, a bit. When the derivative I had over here was for the KL divergence with respect to the output of the network. But then what we actually do is this. We first compute these affine terms Z. And then you put the affine term Z through a softmax to compute the network output Y. And then you're computing the divergence between the network output Y and the desired output. Now, instead of computing the derivative of the divergence with respect to the output of the network, what would you get if you computed the derivative of the divergence with respect to the affine term that went into the softmax? And it turns out that if you compute the derivative of the KL divergence with respect to the Z rather than the Y, that simply becomes Y minus D. Does this look familiar? Why does it look familiar? This was exactly the same as the derivative of the L2 divergence. And so here's what you have. When you're performing regression, you generally have an identity as the activation function for the output layer. When you're performing classification, you generally have a softmax activation at the output layer, right? Regardless of which task you're performing, if you compute the derivative of the loss with respect to the affine term, that simply ends up being the error between the actual output of the network and the desired output of the network, Y minus D. So that's why the derivative is just the error. So back in the day, when we spoke of computing derivatives and then moving them backward through the network to using the chain rule, we call this error backpropagation. And it's error backpropagation because regardless of what you're performing, whether you're performing regression or whether you're performing classification, the derivative at the very output of the network is simply the error. And this is what you're moving back through the network. So again, this is something you want to remember, that the derivative of the divergence with respect to the affine terms, Z, is always the error between the output of the network, post-activation output of the network, and the desired output. Okay? You guys awake enough to get that? Because it's going to come in class. All right. Can everybody say yes?
Yes.
Thank you. All right, so all terms have been defined once we've done this. Here's your final poll to make sure you're awake. That's a very interesting name, Ursering. Okay.
I want to say it in this time.
Okay, you can go ahead and pronounce it.
Oh, what was it again? Can I read it?
All right, Jeffrey is going to read this.
Ursering.
Who's Ursering? Ursering's absent, okay. Who's
Polyrath.
Who's Polyrath? Polyrath is also absent, okay. And Swablu again. Who's Swablu? We know Swablu's absent. Okay, anyway, guys.
Sorry, do you mean Horsey?
Okay, SWABLU, Swablu. So can you give me the answer to this question? Anybody? Select all that are correct. Is the first statement true, guys? The gradient will always be 0 or close to 0 at the minimum. True or false?
False.
Okay. It may be 0 or close to 0 at a minimum. True, right? It may have a large magnitude at the minimum. True, we saw this, right? So if the gradient is not 0 at a minimum, it must be a local minimum. True or false?
False.
No statement, right? So very good. You have the answers. And so here's the story so far. We've seen that neural networks are universal approximators. They are trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual and desired outputs had training instances. To train them, we have to define inputs, the network, and the divergence. And the divergence, and once you define these, we know how to train the network. We're going to use gradient descent. We'll talk about this in the next class. Thank you.